Alright, today we start a new chapter, which means there's only 3 chapters left in the year already. Sequences, series, and then we start calculus. First of all, what is a sequence? Well, a sequence basically is a function, except the domain is going to be the positive integers, like 1, 2, 3, 4, 5. Because when you have a sequence, you have a first term, you have a second term, you have a third term, a fourth term. There's no such thing as a 2.5 term or a pi term. So that's why the domain is the positive integers, 1, 2, 3, 4, 5. So sequences kind of look like this. A sub n equals, let's just do a simple one, 3n minus 2. That's the same thing as f of x is equal to 3x minus 2. Except the reason why we use n is because the domain is the positive integers. So if I ask you, write out the first 5 terms of this sequence, what would you do? You plug in 1, 2, 3, 4, 5. So if you plug in 1, you get what? You got to be able to plug in numbers, you know. 1, if you plug in 2, plug in 3, 4, 5. There you go, that's the first 5 terms of the sequence. You simply plug in positive integers, 1, 2, 3, 4, 5. There's a first term, second term, third term, and so forth. Now, 2 sequences that you should have learned last year. I'm not sure if you did, but it doesn't matter. If you were in the SAT prep class, we learned it. There's the 2 that you learned in Algebra 2 are the arithmetic sequence. Arithmetic. Now, it looks like arithmetic, but when you use it in the context of sequences, it's called arithmetic. Our arithmetic sequence has a common difference. In other words, you keep adding the same number every time. Like this one over here. To get from one term to the next, don't you just keep adding 3 every time? So if you keep adding the same number every time, we call that an arithmetic sequence. It has a common difference. Now the formula for an arithmetic sequence is this. A sub n is equal to a sub 1 plus n minus 1d. So let's define all the terms. A sub 1 is the first term, right? Because when you write out a sequence, you have a sub 1, a sub 2, a sub 3, and so forth, right? First term, second term, third term. A sub 1 is the first term. N is your independent variable. It's kind of like x. And d is the common difference. So for example, you have this sequence over here. It's arithmetic. What if I ask you to write the explicit formula for the sequence? Then you just simply do this. A sub 1 is the first term, 1. Then you write n minus 1, and then you just ask yourself, what is d? What is the common difference? What number do I have to keep adding every time? 3. And there you go. That's your formula. We call that an explicit formula. And you probably want to simplify that, so if you distributize the 3, you're going to get 3n minus 3 plus 1 minus 2. That's called the explicit formula. An explicit formula is a formula where if you want the 10th term, you simply plug in 10. If you want the 20th term, plug in 20. And look, see, same thing like that. Okay, let's do another one. How about, 4, 10, 16, 22, 28, dot, dot, dot. Is this an arithmetic sequence? Do I keep adding the same number every time? Come on, people.
Yes.
Yes. So you use the formula. A sub 1 equals the first term, 4, plus n minus 1 times 6. Right? Because isn't 6 the number you keep adding? 6 is called the common difference. And there you go. That's the formula. And if you distributize the 6, what do you get? You get 6n minus 2. Now, since we're in honors, you see, this formula is good because you're going to have to use it sometimes, but to write the explicit formula, we can kind of save common difference is, isn't that this number here? Yes, see, because this is just a simple linear equation. So once you know the common difference, instead of going through this formula, you can just do this, right? 6n, and then you adjust it. Like, in other words, if you plug in 1 for n, shouldn't you get the first term? So if I plug in 1 for n there, what is 6 times 1? 6. What do I have to do to 6 to get 4? Subtract 2. See, it's the same thing. You can only do that when it's arithmetic, though. So here, let's try to use that on a different sequence. So what if you had 2, 7, 12, 17, 22, dot, dot, dot. How would you write the explicit formula? Well, what's the common difference? 5. So you write 5n, and then you adjust. If I plug in 1, I want to get 2. 5 times 1 is what? 5. What do I have to do to 5 to get 2? Subtract 3. It's up to you. I'm just teaching you a shortcut there. If you rather just use the formula, you're going to get the same thing. Now, the other type of sequence that we should have learned last year is geometric. These are the two that show up on the SAT and the ACT anyway. A geometric sequence. A geometric sequence has a common ratio. In other words, you keep multiplying by the same number. And here is the formula. A sub n is equal to a sub 1 r to the n minus 1. Okay, let's look at an example of a geometric sequence, like 3, 6, 12, 24, 48, dot, dot, dot. So when you first see a sequence, the first thing you ask yourself, is it arithmetic? No, I don't keep adding the same number. Do I keep multiplying by the same number? Yeah, you keep multiplying by 2. So when you keep multiplying by the same number, that's called a geometric sequence. And if I ask you to write the explicit formula for it, you just follow this formula. A sub 1 is the first term. 3. R is the common ratio, which is the number that you keep multiplying by, which is 2 into the n minus 1. And there it is. That's how simple the formula is. And does it work? If I plug in 1, do I get this? Yeah. If I plug in 2 for n, do I get this? Yeah. Why would we teach you a formula that doesn't work? Okay, let's look at another geometric sequence. How about something like this? 8, negative 4, 2, negative 1, 1/2, negative 1/4, dot, dot, dot. What is the explicit formula for this sequence? Well, a sub n equals, what's the first term? E. What is r? What number do I have to keep multiplying by to get the next term? Negative half to the n minus 1. And that's the formula. But of course, if you can simplify it, you should simplify it, because can't that be simplified? Right? Because isn't this like 2 to the third? They have a common base, that's why, right? Oh boy. See, look, 2 to the third. And what is negative half? Isn't that the same thing as negative 2 to the negative 1? Yeah, to the n minus 1. And what do you do with the exponents?
Multiply.
You multiply, so you get 2 to the third times negative 2 to the
1 minus
negative n plus 1. And then can't I just take the negative sign? A positive times a negative is a negative, right? 2 to the third times 2 to the negative n plus 1. And then what do you do with the exponents? You add the exponents. So you get negative 2 to the
negative n plus 4.
negative n plus 4, or 4 minus n. Wait, that doesn't look right, yeah? Something's wrong there. Because if you plug in 1, you don't get 8. Something's wrong. What did I do? Somebody tell me, what did I do wrong? 4-digit numbers are not divisible by 11? Why don't we just change that a little bit? How many 3-digit numbers? How many 3-digit numbers are divisible by, give me a number. 7 then. What do you have up there? 11, okay, 7. Okay, what's the smallest 3-digit number that's divisible by 7? 100.
105.
105, okay, thank you. Everybody agree? Can 7 go into that? Okay, then what's the next one? 100, you add 7 to it, 112, add another 7, 119, all the way till, what is the biggest 3-digit number that's divisible by 7? You might have to do a guess and check kind of thing. 900 what? Higa, you said something? 990. Take a guess. Okay, what? So if you don't know, take a guess and then try to figure it out, man. 990? Okay, somebody said 4. Okay, well, let's try. 994 divided by 7. 7 goes into 9 one time. Remainder 2. 7 goes into 29. 4 times the remainder 1, and you get 2. Yeah. 994 is the biggest. So the question is, how many 3-digit numbers are divisible by 7? Well, that's the same thing as asking how many terms are there in this sequence, right? Well, is this an arithmetic sequence? Yeah, because you keep on adding 7 every time, which means you can use this formula, right? A1 plus n minus 1b. Some of you, I bet you could just figure it out, but if you have a formula, it's a lot easier. What do I plug in for a sub n? This is the nth term, except we just don't know what n is. What is the nth term? This, 994. What is a sub 1? The first term, 105. Now what is d? 7. If you solve this equation, you will find out what n is. That's the nth term. So n will tell you how many terms there are in this sequence. Okay, how would you solve this equation? Well, the first thing I would do, I would subtract 105, and you get, you're going to have to borrow. 889 equals n minus 1 times 7. I would divide by 7. So 889 divided by 7, 1 remainder, 2, 4 remainder, 7. So divide by 7, you get 127 equal n minus 1, therefore n equals 128. This is the 128th term, which means there's 128 terms. That's how you do problem 5 over there. Okay, so if, like I said, if the problem has an arithmetic or a geometric sequence, we have formulas for that. Well, what happens when the sequence is not arithmetic or geometric? What do? You use your mathematical prowess, all the math experience that you've gained over the years. Okay, so let's look at some that are not arithmetic or geometric. Let's start with an easy one. How about this? 1, 4, 9, 16, 25, ... Now, of course, in elementary school, they'll probably give you something like this, and they'll ask you, what is the next term in this sequence? People, we already finished elementary school. Look, what's the pattern? Oh, I add 3, I add 5, I add 7, add 9, so the next one will be add 11, you get 36, right?
Yeah.
Oh boy. Yeah, but this is not elementary school anymore. I'll probably ask you on the test, what is the 1,000th term? Now, are you going to keep counting until you get to 1,000? No, if somebody asks you to find like the 100th term or the 1,000th term, what you want to do is get an explicit formula and then plug in 100. Okay, like I said, this is an easy one. Do you guys see it? These are numbers that you should know.
Perfect squares.
Okay, the square numbers. Isn't this like 1 squared, 2 squared, 3 squared, 4, 5 squared, 6 squared, 7 squared, more? Yeah, so what would the explicit formula for that be? N squared, right? 1 squared, 2 squared, those are the square numbers. This was the easy one, people. I can't believe I'm explaining that one. Oh boy. Hey, what kind of mathematical prowess do we have? Okay, like if this is the continuum of mathematical prowess, what do we have?
Negative.
Like a monocle. Is that you? Come on, we're in honors. You should be over here somewhere. Not over here. You should be over there. Okay, we gotta do some more then. Oh gosh, there's so many. Oh no. Oh no. Okay, wait, you guys think you're good yet? Really not yet. Okay, here. Okay, elementary school, they would ask you, what is the next term in this sequence? Okay, can we at least do the elementary school part? Why? Why is it 54? Okay, so she said add 4, add 6, add 8, add 10, add 12. So the next one will be add 14.
56.
So 56 then. 56 would be the next term. Okay, but we're past elementary school. I want the explicit formula, so like if I ask you to find a 100 term, because you don't want to just keep doing that to 100, what about 1,000 term? There's no way you can do that. That's why we want an explicit formula, so you can just plug in 100 or 1,000, whatever it is. Anybody want to give it a go? So what you gotta do sometimes is you gotta break down the sequence. Like, when you see 2, don't you think 1 times 2? Apparently not. What about 6? 2 times 3, 3 times 4, 4 times 5, 5 times 6, 6 times 7. That's called breaking it down. You ever heard of breaking it down now? Oh, that's what this is. Okay, so how do you generate the numbers 1, 2, 3, 4? Isn't that just n? And then how do you generate the numbers 2, 3, 4, 5? Isn't that n plus 1? And then there's your explicit formula. N times n plus 1. You gotta break it down. But see, sometimes it's very difficult to break it down, so we gotta learn all kinds of stuff in this chapter. Oh boy. Okay, here. These numbers come up, this is very important, these numbers. 1, 3, 7, 15, 31, 63. Now, if I ask you for the next number, I'm pretty sure you could, well, I don't know anymore. I'm pretty sure you could give me the next number. Look for a pattern. To get from here to here, you add 2. To get from there to there, you add 4. To get from there to there, you add 8. To get from there to there, you add 16. To get from there to there, you add 32. Is there a pattern to those numbers? Yeah, but I don't know what that pattern is. Those are the powers of 2, right? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So the next one you're going to add 2 to the sixth, so the next number would be 127. Okay, but like I said, we're not in elementary school anymore. What is the explicit formula for this sequence? Okay, why, did you see this one before, or you just figured it out? See, that's what we gotta do. 2 to the n minus 1. Did you guys notice that these are all numbers that are 1 smaller than something? This number is 1 smaller than 2. This number is 1 smaller than 4. 8, 16, 32. Hey, that's the powers of 2. No, over your mathematical career, you experience numbers, right? So like when you see numbers, you go, hey, you somebody. I'm telling you, this one's very important. You will see. Or how about this? Every time we do something on the board, you remember it then. That'll be part of your experience then. Okay, I don't know where to go, because like, oh my goodness, I don't know. Okay, here, you guys better get this one. One. Yeah. Dot. Now, okay, let's prove that at least we can do elementary school math. What is the next number in this sequence?
720.
Okay, see, it's 720. That's correct. How did you do it?
So like multiply, or when you multiply, like number goes up each time.
Okay, so you think of, so like those problems there, we thought of adding, right? But over here, you think multiply. What do I have to multiply to get from here to here? 1, then to get from there to there, multiply by 2. There to there, multiply by 3, multiply by 4, multiply by 5. So the next one you gotta multiply by 6 to get 720. But like I said, we not elementary school. What is the explicit formula? Like if I want the 100th term, I just plug in 100. Where have I seen these numbers before? Okay, I'm going to give you a hint. Oh, why am I? You're not going to get hints. It rhymes with factorial. Okay, so. Do you guys.
Oh.
Hey, Mr. Park, this is 6 factorial, 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial, that's 0 factorial, if you want to follow the pattern. Remember, 0 factorial is 1. So basically, once you know that these are the factorial numbers, how do you generate the numbers 0, 1, 2, 3, and so forth?
N minus 1.
N minus 1 factorial. Okay, maybe we gotta go backwards, yeah? Okay, what about this? 1/2. Okay, we don't want to make it too easy. 1/2, 3/5, 5/8, 7/11, 9/14, dot. What is the explicit formula for this sequence? Now, if you were to like ask yourself, what do I have to add to this to get to that? You're gonna drive yourself crazy, right? Because then you guys know how you guys are with fractions, right? Or what do I have to multiply this by to get that one? So sometimes when you see fractions, you might want to look at the numerator and denominator separately. So let's look at the numerator. 1, 3, 5, 7, 9.
1 plus 2.
Ding, that's arithmetic. What's the common difference?
2.
2, so you write 2n and then adjust.
Minus 1.
2n minus 1. See, that's why it's good to be able to do that. Now look at the denominators. 2, 5, 8, 11, 14. Hey, that's arithmetic. What's the common difference?
3.
3n, and then you adjust.
Minus 1.
Minus 1. There you go. That's the explicit formula. So that's why you gotta look at different things. Sometimes you gotta look at numerator. It's all different. That's why you gotta have some mathematical prowess. Okay. Okay, here. Okay, I'll think of one. How about 1, -8, positive 27, negative 64, positive 125, dot. And what the heck, negative 216, dot. What's the first thing you notice about this sequence? It goes positive, negative, positive, negative, positive, negative. We call that alternating. So this is an alternating sequence. Now, how can I make something alternate positive, negative, positive, negative, positive, negative? Okay, but then we gotta write an explicit formula. See, anytime you have to do something that deals with the term before it, that's called a recursive formula. But we're not gonna learn that until the next time. We're looking at an explicit formula here. So, what's a formula that can make something go positive, negative, positive, negative? I'll give you a hint then. Negative 1 raised to the, I'll give you a hint. Is it n or n plus 1? And what would the difference be?
N plus 1.
Okay, let's say it's n. What happens when you plug in 1 for n? You get negative 1. What happens when you plug in 2? You get positive 1. See how this makes it alternate positive, negative, positive, negative? Okay, but we want it to start positive though, so negative 1 to the n plus 1. Or you could go n minus 1. Actually, n plus or minus any odd number would work as well, yeah? So this, you gotta get used to this in calculus. It comes up all the time. This makes it alternate, okay? So that, we took care of that. Now just look at the numbers. 1, 8, 27, 64. Somebody said it, Higa. Those are the cube numbers, right? 1 cube, 2 cube, 3 cube, 4, 5 cube, 6 cube, 7 cube, more. So n cubed. Okay, we gotta look some more, because I have some other ones. You know what? We're gonna go there already. Okay, so this thing, negative 1, a sub n is negative 1 to the n plus 1. That makes it go 1, negative 1, 1, negative 1, 1, negative 1, dot, dot, dot. But is there another way to write this as an explicit sequence? Yeah, because you know what? On the quiz, I'm going to give you a problem like this. A sub n is equal to cosine. So I'm going to give you the sequence, and then I'm going to tell you, fill in the box. What has to go in the box to generate the terms of that sequence? Okay, let me ask you this. Cosine of what will give you 1? 0. Cosine of what will give you negative 1? Pi. Cosine of what will give you positive 1 again? 2 pi. Oh shoot, I forgot to write the cosine. Cosine of what will give you negative 1? Cosine 3 pi. Right? So we can kind of think of this as 0 pi, think of that as 1 pi, right? So basically all the only numbers that change are 0, 1, 2, 3. So how do you generate the numbers 1, 2, 3, 4, and so forth?
N minus 1.
I mean, yeah, starting with 0. So n minus 1, right? So it's going to be n minus 1 pi. Mr. Pergana liked it. And then I might give you this. What about sine? Fill in the box. So what you do what I did up here. Sine of what angle will give you positive 1? Pi over 2. Sine of what angle will give you negative 1? 3 pi over 2. Sine of what angle is positive 1 again? 5 pi over 2. Sine of 7 pi over 2 is also negative 1, and then it just alternates. And is there a pattern to these numbers here? Look at this. 1, 3, 5, 7. Yeah, those are the odd numbers. So what do I put in the box? How do you generate 1, 3, 5, 7? Basically, that's all it is, right? Everything else is the same. These are the only numbers that are changing. What's the common difference? 2. So you write 2n and then adjust. 2n minus 1, and then pi over 2. And then, of course, you know what's coming. Tangent. Okay? So, what if I tell you, okay, take this sequence here, fill in the box to generate an explicit formula. Okay, so what do? You write this. Tangent of what angle will give you 1? Pi over 4. Tangent of what angle will give you the negative 1? Mr. Park, if I knew my trig values, I would know. Tangent of what angle will give you positive 1? 5 pi over 4. And of course, negative 1, that's tangent 7 pi over 4. Is there a pattern to this, or these are just random things? There's a pattern. Basically, the pattern is 1, 3, 5, 7. That's what this is. We already did it. How do you generate the numbers 1, 3, 5, 7? We just did it up here. Look, it's right there. 2n minus 1, and then what do time, or maybe I should teach you today. Depends. Okay, look at this. Okay, this is not that easy. Okay, I'm going to tell you that right now. But let's see if you can break it down. Try breaking it down. Even to find the next term, it's not going to be that easy. This is a tough one. Okay, I'll give you a hint. It has something to do with cubes, cube numbers. Okay, like 1 cubed. What does this have to do with 1? 2 cubed. What does this have to do with 2? 3 cubed. 4 cubed. Cruise.
N cubed minus n.
There you go. See, so you gotta play around with it. You gotta go, okay, oh, this is 1 cubed minus 1. 2 cubed minus 2. 3 cubed minus 3. 4 cubed minus 4. That's called breaking it down. Hey, I see the pattern. It's n cubed minus n. Or, another way you could have done this is, I don't know if you think about this as, look, hey, 6. Isn't that 1 times 2 times 3? 24 is 2 times 3 times 4. What is 60? Isn't that 3 times 4 times 5? What about 120? Is that 4 times 5 times 6? Is there a pattern to this, or these are just random numbers? There's a pattern, so to follow the pattern, what would this first one be?
0 times
0 times 1 times 2, right? So how do you generate the numbers 0, 1, 2, 3? N minus 1. How do you generate the numbers 1, 2, 3? N. And then how do you generate the numbers 2, 3, 4? N plus 1. Is that the same thing as that?
Yes.
Yeah, so that's just another way that you can break it down. Okay, here's another, I'm going to tell you, this one's going to come up a lot from now till you finish calculus. We already had it before, but I think some of you forgot. Not I think, I know. What is the next number in this sequence? Mr. Parker, I like the elementary school ones. 21, right? Because you add 2, you add 3, you add 4, you add 5, so the next one you add 6, right? Okay, but I told you we had this twice before. These are numbers that are very special in mathematics. The triangular numbers. Do I have to explain why they're triangular again? Okay, I don't want to. And I told you guys to remember the formula for it. Tanaka. There you go. N times n plus 1 over 2. I'm telling you, I guarantee you this is going to be on the quiz and the test. It's going to be in future quizzes and tests. And it's going to be next year in calculus too. Now, if you're not going to remember this, then you got to break it down. Like you got to say, hey, isn't this 1 times 2 over 2? 2 times 3 over 2. 3 times 4 over 2. 4 times 5 over 2. You break it down and then you can do this. But I think it's a lot easier to just memorize the triangular numbers. You know what? Usually I wait till later to teach you, but I'm just going to teach you today already. Because some of you are saying, Mr. Park, I cannot break that down. In fact, even the easy ones, Mr. Park, I cannot break down. Okay, here. Okay, I'm going to think of one. No. Okay, like this. I made it kind of simple. Can you guys break that down? Like when you see 8, what do you think? I want to go to sleep. I don't know, I think 2 times 4 and then 3 times 5. Oh, so this is like 1 times 3, 4 times 6, 5 times 7. So what's the explicit formula? generate the numbers 1? See, if I keep telling you, then you're not going to get it, right? How do you generate the numbers 1, 2, 3, 4, and so forth? N. How do you generate the numbers 3, 4, 5? N plus 2, and there you go. That's your formula. But Mr. Park, what if I can't break it down? What am I going to do? Am I going to fail this chapter? No, because I'm going to show you something now. But you have to do work, unfortunately. Okay, so what you do is, when you see a sequence and you just can't break it down, because is it arithmetic or geometric? No, it's not, because if it were, there's a formula, right? So what you do is you look at the differences. What are the differences of these numbers? 5, 7, 9, 11, and the next one would be 13, right? Now look at the difference of the differences. 2, 2, 2, 2, 2. Now if it takes 2 levels to get to a constant difference, then you know the formula is going to be a second-degree polynomial. You know what I'm talking about? Just like if it only took 1 level to get to a constant difference, then it would be a polynomial of degree 1. If it takes 3 levels, it's going to be a third-degree polynomial and so forth. So we know the formula is good, since it took 2 levels, is going to be a second-degree polynomial. That means the highest power is 2. an squared plus bn plus c. And then now we can just write equations and mechanically solve it. Okay, how do I do this? Well, if this is the formula, if I plug in 1, shouldn't I get the first term then? This is the first term here. So plug in 1. What happens if I plug in 1 for n? You get a plus b plus c. That should equal to the first term. If you plug in 2 for n, you should get the second term. And if you plug in 3 for n, you should get the third term, right? Okay, plug in 2 for n. What do you get?
4a.
4a plus 2b plus c. That should equal to the second term. And then if you plug in 3 for n, which is 9a plus 3b plus c, that should equal to the third term. If you solve these equations, that will tell you what a, b, and c are. Okay, let's try. Now, if I were to solve these equations, this is what I would do. Since the coefficients of c are all 1, if you just subtract the equations, the c's will disappear. So I would go, if you call these equations 1, 2, and 3, I would go 2 minus 1. 2 minus 1. 3a plus b equal 5. Now you have to involve equation 3, so you can either go 3 minus 1 or 3 minus 2. I like to go 3 minus 2 because they're next to each other, so there's less chance of making error. What is 3 minus 2?
5a.
5a plus b equal 7. And then now you can just go this minus this.
2a equals 2.
2a equal 2, which means a equals
1.
1. And of course, once you get a equal 1, plug it back into one of these.
b equals 2.
B equals 2. And once you got a and b, plug it back into one of these to figure out c.
0.
C is 0. So that means your formula was 1n squared plus 2n plus 0. Is that the same thing as that? Yeah, it is. But this is a mechanical way of doing it. So those of you who don't have the big prowess to break down the numbers, then that's what you got to do. At least it's a mechanical way of you getting for you to get it. This is called the method of finite differences. See, you look at the differences until it's all the same number. Okay, I taught that to you now, so that'll make it easier in the future. Save time for later. Okay, so this chapter is usually not that difficult, but okay, so this is like one of the things you got to get used to. And then another thing you're going to have to get used to in the second half of the chapter is you got to remember all your base graphs and things like that, as usual. Oh no, base graphs. Like if I told you one base graph, okay, let's just do a test here. Y equal cotan inverse x. I think you guys knew it on the semester exam, and you're going to have to know it again. See, if I draw this graph for you, again, remember, when I draw the graph, I remember the range, 0 to pi. Remember the two ranges? And then I think of graphs on the cotangent graph, and I switch it to get the inverse. So it looks like this. You know why this is important in calculus? Because in calculus, you have to know, like, if you're given a function, what happens to the graph as it's going out to the left? In other words, what is the limit as x approaches negative infinity? And then what's happening to the graph when it's going out to the right? What is the limit as x approaches positive infinity? So like if I have the graph in front of you, you guys should be able to do it. As the graph goes out to the left, the y-coordinates are getting closer to what number? Pi. As the graph is going out to the right, then the y-coordinates are getting closer to what number? 0. That's what calculus is right there. So that's why we stress base graphs throughout your mathematical career, because they're really important. All of calculus is based on this thing right here, limits. And you will see that after we finish the chapter after this one. Okay, let's worry about this. Oh, one last thing. When you're working with arithmetic and geometric sequences, it's important to be able to label them now. So how would you label, because sometimes the sequence is unknown, so you have to start writing equations to figure it out. How would you label an arithmetic sequence? There, like this. Okay, I'll tell you. A plus D, A plus 2D, A plus 3D, dot, dot, dot. You guys see how that works? A is the first term, and then you just keep adding D every time. Now, you don't have to use these variables, but it's up to you. But that's what you have to do. How would you label a geometric sequence if the first term is A? Geometric means you keep multiplying by the same number, except we just don't know what the number is. AR, for the ratio, that's why. AR squared, AR cubed, dot, 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 right? You keep multiplying by R. That's how you label, because you're going to have to do that in problem number 7. And then Mr. Park, I'm looking at number 6. I see the word logarithms. Yeah. We're going to practice our properties of logarithms. All right, that's good enough for today. Okay, this class ends in 5 minutes. Yeah, maybe you should try the first problem.